moving forwards into our exploration of electric fields, we're now going to look at equipotential surfaces. It's going to take a little bit of explaining to get to the final point. And in order to do so, you can see there on the left hand side we've got a uniform field. Just want to make a couple of points about uniform fields before we move on. So in this case, with a uniform field, two things that are important to note. The first thing is that the electric field strength has, or the electric field, is constant between these two charge plates. So you can see on the left we've got a positively charged plate, and on the right is a negatively charged plate, and the pink lines there showing the electric field strength in between the plates, or the electric field in between the plates. The electric field strength is constant because the spacing of the field lines is the same. If you then note on the edge, we can see that there's a bit of a bend in those field lines, and they bend even further the further away you get. At the edge of a uniform field, you'll usually see that the electric field strength becomes weaker, and this so if we look at the extremes of the field, that's commonly referred to as edge effects. So just something to note that if we're dealing with a uniform field, we're really dealing with the middle of the uniform field, so we'd be dealing with this sort of region through here, not the edge, or not where the edge effects come into play. So just point to note about uniform fields. As we go through with equipotential surfaces, it's a little bit easier to explain in terms of by using uniform fields. We will then extend that to look at other fields around other scenarios when we get back into class. So to take this a step further then, if you are moving a charge in a field, so whether it's a uniform field or not, work is only going to be done when you move against the field. So if you were to move a charge, in this case a positive charge, so if we'll deal with a positive charge, given that electric fields are about what happens to a small positive test charge. So if we were to move a positive charge against the field, that's when work is going to be done. And by against the field, what I mean is that it's in the opposite direction to the field lines. So if we were to take a charge that was, say, a small positive charge that was, say, here somewhere, and we were to do work on it, that would mean that we're moving that charge in that direction there. So work's only done when you move against the field. So for a uniform field, in this particular case, we'd need to move that charge to the left. So you can see the field lines directed to the right, so in order to do work on that charge, we've got to move that charge to the left. If we know the quantity of that charge, we can then figure out what the potential difference is. So I'll just make that note. So if the quantity of charge is known, we can then determine what the potential difference is as we move through that field. And we can determine that by using the equation that we saw in the previous video. And that equation is in the form, sorry, let me spell that correctly first. If you may recall that the potential difference is going to be equal to the work divided by the charge. Now in the data booklet, that for Unit 10, that equation has been reformatted to particularly focus on the amount of work that's being done, and so that will be W is equal to Q times the potential difference. So that particular equation is one to be familiar with, and as I said, it's just a rearrangement of the previous equation we saw for potential difference. So if we know the potential difference, we can then make some more comments about what's happening in the field. Now, if you look at this situation, you can see that if we were to move the charge from the negative plate all the way across to the positive plate, then we are going to have a potential difference that's equal to the potential difference between the plates. If instead we were only to move that charge, say, halfway across, as that arrow kind of indicates there, then the potential difference at that point is only going to be half of the total potential. So at that point it would be V on 2, not V. And that then leads us to this idea of equipotentials. So if we were to repeat that, let's say we then used a charge that was here somewhere and another charge that was here, and we were to do enough work on it to move it halfway across, what we would find is that in each case the electric potential at those points is always going to be V on 2. So if we were to repeat that for any charge at any point on the negatively charged plate, then we would, if we applied or did the certain amount of work that meant that we had a potential difference of V on 2, all of those charges would end up halfway across in between those two plates. So if we then look at all of the points that have the same potential difference from the negative plate, whether that's V on 2 or some other value, but with the same potential difference, notice that we're using the negative plate as our reference point. That's a key thing that we'll come back to a bit later. So same potential difference from the negative plate. Those points are called equipotentials. And if you look at that word, it's sort of fairly easy to figure out what it means. Equi meaning equal, and potentials being electric potential. So all of the points that have the same potential difference from the negative plate, they're known as equipotentials. In this case, if we were to look at all of the points that have the potential of V on 2, we'd find that they all end up at this point straight down in between the middle of the two plates. So that would be, that line there represents the points that all have the potential difference of V on 2 from the negative plate. Notice there, if we do look at that point that's straight down the middle of the plates, it's no longer just a series of points. It actually now turns into a straight line in this diagram. But if you imagine two plates that are sort of going, I suppose, coming out of the page here, that line down the middle actually represents a plane or a surface. So rather than just talk about equipotentials, we can talk about equipotential surfaces. Now, there are a few key points that we need to make about equipotential surfaces. And they are as follows. The first one, as we've already just identified, they link points that have the same electric potential. Note that we're using the term there, electric potential. The reason for that is that when we're talking about equipotential surfaces, we should always refer to them corresponding to some zero potential. And in this case, the zero potential would be the negative plate. So when we're dealing with potential surfaces, we can only really talk about them in the context of having a zero potential. In other examples, that zero potential will change. And in fact, we could, in this scenario, instead of using the negative plate as the zero potential, we could use the positive plate as the zero potential, which would mean that the negative plate would then be a negative potential. We can talk about that more in class. But ultimately we need to make sure we have a reference point that is at a zero potential. Now, a couple of other things that useful to note here. If we think about doing work against the field, that means that all of these charges, when they have moved to this potential of V on 2, we could move those charges along that equipotential surface, and we're not actually doing any work on it because it's now moving perpendicular to the field. It's not moving parallel to the field, it's not moving against the field, it's now moving perpendicular. So that actually brings up 2 points. So equipotential surfaces are regions where no work is done when the charge moves along the surface. And as I said, the second point is that those equipotential surfaces are at 90 degrees to field lines. So they're always going to be perpendicular to the field lines. Another key point here about equipotential surfaces is that they are scalar quantities. That is, they don't have a direction. So while you can talk about the size of the equipotential surface or the magnitude of the potential at those points, you don't have a direction associated with it. You wouldn't say it's 10 volts to the left or 14 volts down. It's just about the fact that it's either 10 volts or 14 volts. And the last one, that's fairly self-evident, equipotential surfaces can never meet another equipotential surface with a different value. So you can't have an equipotential surface of 10 volts that meets with an equipotential surface of 14 volts. Which is basically just saying that you can't have that 10 doesn't equal 14. Fairly obvious sort of statement. Now, if we go back to this example of the parallel plates, we've kind of already identified what the equipotential surface looks like here. It is, in this case, just a flat plane. We could have another equipotential surface that's down through here somewhere, and another one down through here. So this one would be, say, V on 4, and this one would be 3V on 4. So that means that if the potential here, EMF here was 12 volts, then down the middle it would be 6 volts, over on the right hand side it would be 3, and over on the left hand side it would be 9. To finish off, what we're going to look at in class are a couple of other scenarios. So we've identified the easiest one, being uniform fields, where we get equipotential surfaces that are just flat planes. In class we'll have a look at the equipotential surfaces around a singular point charge, and you might want to have a think about these before you come into class. So a singular point charge, 2 point charges that are close to each other. Third one would be the equipotential surfaces as related to a charged sphere. Another one that's fairly common is a coaxial conductor. So that's basically 2 conductors, one wrapped around the other. And finally, a point charge near a charge plate. And if you want to have a look at these ahead of time, they are in the text, but we will go through them in class and sort of help you to develop your understanding of these ideas.